Hello everyone, welcome to the second part. So in this portion, we're going to talk about a few concepts that's related to the applications. So first, I'm going to talk about the marginal cost, the revenue, and profit. So it is a very widely used concept. So when we do the marginal analysis, right, marginal analysis, which means that what is the additional cost or additional revenue or additional profits given there's a slight change or slight increase, right, slight increase in my inputs. So this is to say how sensitive my output is given the change in the input. So for example, we have the total cost, C of X, and then we can express the marginal cost just as the derivative or first derivative of the cost function. So we have the revenue as well, first derivative. We have total profits expressed as the revenue minus the cost. And then we just take the first derivative to get the marginal revenue minus the marginal cost, all right? So let's look at the cost analysis. So the marginal cost, which is the first derivative of the cost function, and so that's one entity. And we also have another entity which calls the exact cost. When x moves, so when x changes from x to x plus 1, right? So this is an entity, and want to compare these two entities. So why are we interested in this? Because we know that the C prime of X, so the cost function is actually exactly the cost difference, right? The exact cost difference average across the interval. The interval is X plus 1 minus X, right? Which is just 1. And then we're adding a limit, which is that's the so in the extreme case, when we actually consider what we're considering is actually a delta x, right? So but in this case, we're actually fixing delta x to 1. So now it's actually 1, and there's no limits. So we want to actually compare the how good is approximation of these two entities, right? So this one is average, another one is the using the derivative to get the differential in cost. So graphically, we have this point here, which is now delta is equal to 1, and we have the starting point, we have the end point here. So this is my end point. And we can express two differences. So first one is the difference in this, so this is the first difference. This is the difference in y-axis using the cost function, right? And then the second difference is the differential in the cost function, right? So which is the first derivative, and we can get the expression for cost, the derivative of the cost function as well, and want to compare these two functions. And if so, the reason is that if we know the first derivative, then we don't need to calculate the expression, right? Just use the first derivative to approximate the second one. And vice versa, if we know this, then we can just use this entity to approximate the derivative. So that's actually equivalent, and assuming that they're actually close or very close to each other. So that also means that the delta x cannot be too big. Otherwise, the approximation is not going to be very good. So let's look at the cost analysis example. So in this example, we're given the cost function. The first question asks, what is the marginal cost function? So we basically just take the derivative of the first function, so to express it out, right? And then the second question asks the marginal cost at production level of 500 tanks per week. What this means is that when we set x equal to 500, now what is the my value for C prime, right? Which is x equals to 500. And then this is something we can also calculate. In terms of the interpretation, so this means that when my x is equal to 500, right? So my x is equal to 500 tanks per week. Now, what is the rate of increase, right? Rate of increase for the cost. Because if we produce more, then the cost gonna be more, and we want to know what is the marginal or additional cost, increasing cost when we actually produce more tanks, right? So at the production level, which is 500. So that also means that's what is the additional cost, right? We expect it to be the when we take the five or one more additional tank, and how much cost would that incur to me, right? So now finally, I want to compare that with the exact cost. So the exact cost again is something we can calculate, right? So we can say this is the cost of producing 501 tanks, and we have the cost of producing 500, and this gives us the delta X, delta C, right? Delta C, which is the cost, the exact cost of producing the 501 and one tanks, right? So this is how we can calculate. All right. So marginal average cost, revenue, and profit. So this is where we actually introduced the notion of average. So how to get average, right? Average just a quantity, which is cost in this case, averaged over some interval, right? This interval is x, so just C over x. And the marginal average cost is again still the average cost, but we're actually taking the function, taking the derivative of this average function. So this is how we can calculate it. And similarly, we have the marginal average revenue and marginal average profit, right? So again, in terms of the exact analysis, now we have two candidates. This is something I can calculate because we can just plug in the definition of the average cost and then take the derivative and then evaluate at least 2 points to get the exact quantities, right? So we can interpret this quantity as well. And then, so basically what this means is that now at the production level, right? So we have different production level in terms of the input. So input is the production of producing X bits. So when we produce 10 bits, for example, right? And then what is the additional cost if we were to produce one more bit, right? So this is how we can calculate, and we can use the results from B, which is the derivative, right? The marginal average cost to estimate the average cost per bit at production level, which is 11. So again, we can get the additional cost by just using the derivative to approximate the actual cost. So this is where the approximation comes in, right? So we can get the new cost and then the old cost and then do the approximation. So based on the derivative here, then we can just say this is using the derivative, first level derivative to approximate the actual marginal cost. All right, so now let's look at the one more application, which is the related rates. So this is so this is concerning two variables, right, x and y. So we have this equation here, and we want to know, for example, how fast y coordinates is changing at that moment when x is changing. So how is x changing? X coordinates increasing at the rate of 0.4 per second. So this is my x changing x, right? So in other words, now when x changes with respect to time, so t is for time, now it's changing at 0.4, right? So this is given, and we have a point which is -3 and 4. So this is also given, and we have this equation here. So given this, then what we can use is to use the implicit differentiation, right? So we can differentiate implicitly both sides. So we can get equation, and then we can plug the numbers to get the dy over dt. So this is our target want to solve, and just plug in numbers can solve for the relative change in y, which is the related rates, because now there are two variables involved. All right, so that's just some analysis on the question, and And we have one more related concept, which is the relative rate of change. So again, this built on the rate of change, and is also now we have one more entity, which is the relative, which is we need to divide by the original function itself. Why is that the case? Because we want to know, given the change we have, the rate of change or the change in y, and I want to know how much is the proportion of the change, right? So which is called the relative change or the percentage of change, which is multiplied by 100. And it happens that this expression here is equal to the derivative of the ln x, right? So if we take the derivative, then we know that they're actually equal to each other. That also means that we can easily calculate this expression just by taking the derivative of the first one. So we should take the derivative of the ln. So in this case, for example, if we invest this amount of money at an annual rate, this rate, and then compound it continuously, so naturally, this is our this amount of money we'll get, right? And we want to know what is the relative rate of change, right, of this amount in the account. Then we can just take the derivative of the ln of this amount, which will get us some value, right? So this is another related concept. And lastly, we have one more notion, which is elasticity of demand and revenue. So this is one more concept which will be useful sometimes in particular applications. For example, the elasticity of demand versus revenue. This is quantity, right? So if it is within 0 and 1, then it is inelastic. And if it's bigger than 1, and then it's elastic, means that so P is the price. P stands for the price. So if price changes slightly, then what is my impact to the demand? And how does that changes my demands in the products, right? So if it is not very sensitive, means that I can increase my price, right? Price will increase, P increase, and then the revenue also increases. So my revenue also increases. However, if it's so this is the case when, for example, in the industry of diamonds, for example, jewelry, right? So if it's increased in price, then people still buy them. However, if it's very customer sensitive products, daily products like the price of the vegetables or daily products, then if there's a price increase, then that's actually decrease value because customers will compare between products, right? So if there's a even slight change in increase, then it's the change in the demand is very elastic, right? So there will be a huge change in the demand. And then if it's unit to 1, then actually the similar amount of change in price will result in similar amount of change in the demand, right? So that's for the elasticity of demand. And let me just write down the formula here. So this is the piece of price, and then this is F prime P over FP. So how to understand this? So this actually defined as the relative change in demand. Let me just express this change in demand versus relative change in price. And then we have this negative sign here. So relative change in demand, there's something we can calculate, which is this one. So F is my demand function. So this is demand. And relative change in price is, again, let me take the derivative of the ln of price. So we have the ln of P, and then the over P. Then this gives me basically 1 over P, right? So this 1 over T is the property we look at here. So let me just plug in. So we have F prime P over FP divided by 1 over P is a negative. Then we have the expression here, which is the same as here. So basically, this is the definition of the elasticity of demand, and it basically measures the relative change, right? The relative change in demand versus the price. So which one grows faster? So it's comparing the relative scale in the change. All right. So that's it for this class, and thanks for watching.